Okay, and we'll move on to the next speaker, which is Kavitha Arur. And she's going to give a talk using the bispectrum to probe radio X-ray correlations in GRS 1915. And we can see your slides.
Okay, perfect. So yeah, thank you very much for having me at this hybrid conference, and being able to talk virtually is awesome. And with that, I will jump right in.
You could go to full screen, I guess.
Yeah, there we go. Okay, perfect. So yeah, we've already heard a couple of times in this conference how timing studies are a great way to try and understand the accretion process around X-ray binaries. And you talk about timing signatures. One really prominent one that we see are these peaked components in the power spectrum, which are quasi-periodic oscillations, or QPOs, which we've already heard a little bit about. And because of the frequencies at which we detect them indicates that the X-ray emission comes very close to the region, close to the central compact object, QPOs are a great way to probe the accretion process. However, despite knowing about QPOs for a long time now, there is no universal consensus on what the origin is. And that's because we have plenty of models and plenty of classes of models even that can describe the broad features of the power spectrum. And so to break genesis between these models, we need to go beyond the power spectrum to really try and get at what's going on here. And one way to do that is using the bispectrum, which we've already been alluded to a couple of times, like in Ed's talk. But broadly, the bispectrum is a higher order time series analysis technique, and it's the Fourier domain equivalent of the 3-point correlation function, which you might be familiar with. However, unlike in the case of lags of the cross spectrum, which we've heard a lot about in the last couple of days, the bispectrum is calculated using a single time series. So you don't have two different ones and compare between them, just the one. And crucially, the bispectrum is probing interaction between triplets of Fourier frequencies. So in the case here, you have, if you have a Fourier frequency F1 and F2, we're seeing how that interacts with the sum of F1 and F2. So it's all in the same time series here. Rather than the bispectrum itself, it's easier if we talk about the bicoherence, which is a very related statistic, which I will be focusing on for the rest of my talk. And this is analogous to the cross-coherence function that most of you might be familiar with. There is really a lot that I can talk about the bicoherence here, but the real key takeaway is that it is a measure of the strength of the phase coupling between the Fourier frequencies. So how each of these frequencies, the phases of those are coupled to each other is what we're really trying to probe here. And this is information that we do not get from the power spectrum. The bicoherence is normalized to lie between 0 and 1, with 0 indicating the phases are completely random, and 1 being that they are very strongly coupled, perfect coupling. In reality, of course, you get something in between because you don't have infinite amount of data as much as we would like that. So what does it actually look like when you apply it to actual X-ray observations? Here we have an example. In the top panel, you see the power spectrum. You see a very strong QPO there at 3.5 Hertz. And the bottom panel shows the bicoherence. So this is a contour plot, and it shows regions of high phase coupling. So if you see a very strong feature there, the relevant frequencies are phase coupled. So in this case, probably one of the first things that your eye is drawn to is the very strong diagonal line in the bottom left corner. So when the bicoherence looks like this, we call it the hypotenuse pattern. And essentially, that region is indicating that there is interaction between the QPO and the low frequency broadband noise that you see on the left. However, not all bicoherence patterns look like this. Sometimes we get something very different. But my screen has stopped going forward.
Oh, yeah. Oh, your mouse is moving.
Yeah, but it's, well, I will stop sharing and start sharing again.
Yeah. Mm-hmm.
Right, sorry for the technical difficulty there. But yeah, sometimes we see something very different. In this case, we have what's called a cross pattern, because you can see a cross in the bicoherence. And here, these strong vertical and horizontal lines indicate that there is interaction between the QPO and the high frequency broadband noise. And then finally, we can put it all together in the web pattern, which is a hybrid pattern. And as you would expect, here we see interaction between the QPO, the low frequency noise, as well as the high frequency noise. So despite the fact that the power spectrum looks pretty similar in these cases, the bicoherence looks very different. And if you could take one thing away from this talk, it would be that we can see interaction between the QPO and the broadband noise, which means they are not independently generated processes. So you don't have a process that creates the broadband noise and stick a QPO on top. Not quite, it's that simple. They talk to each other somehow. The other thing I would like to point out about the bicoherence is that, like with the QPO amplitude or the phase lags, the bicoherence of QPOs also shows an inclination dependence. So in these sources here, when we looked at a number of QPO observations, we find that at low frequency, pretty much all sources show a web pattern. But as you go to higher QPO frequency, you see either the cross or the hypotenuse, depending on whether we're looking at the system face on or edge on. So now that we're kind of familiar with the terminology that comes with the bispectrum, I'd like to focus on one particular source, which is GRS 1915 plus 105. Now we've already heard a couple of talks about this, and I think we're all familiar that this is a weird and wonderful source. In the light curves, you can see a whole bunch of variability classes, you can see here on the left, and the radio also shows very strong, powerful jets. And I'll add to the mix here by saying that the bicoherence behavior of GRS 1915 is also unique. And it is unique because it is, of the sources we've studied, the only known black hole X-ray binary that shows all three of the patterns that I've discussed. So if we know that GRS 1915 is a high inclination source, so if it was behaving like all the other ones we've looked at, you would expect to see the web pattern at low frequencies, which we do. And you'd expect to see the cross pattern at high QPO frequencies, which we do. But interestingly, we also see the hypotenuse pattern here, which doesn't quite fit into the pictures we get from the other ones. So to see what's going on here and under what conditions we see which pattern, I looked at 90 observations of QPOs from GRS 1915 using RxTE data. And there is really a lot that I can talk about here, but for the sake of time, I'm going to jump to kind of the big takeaway point here, which is...
Okay, you have about 3 minutes left. I was just going to say that was a perfect time. So
perfect. And the key big result here is that we see a strong correlation between what bicoherence we see and the radio properties. So here it's just a plot of the hardness ratio against the QPO frequency. And you can see that the patterns that we see are really clustered in these distinct clumps. For example, at low frequencies, where you see the web pattern is when we also detect radio, if the source is radio bright, but it is also optically thick radio emission. On the other hand, when we see the hypotenuse pattern here, the radio is still bright, but we have optically thin radio emission. And finally, where you see the cross pattern up here is coincident with radio faint observations. So what's going on here and how do we start to make sense of these results? Well, we aren't quite at the stage where we have these really sophisticated simulations that can say, hey, this is what's going on. We can start to develop a bit of an intuition for what is going on physically in the X-ray binary. So for example, the hypotenuse pattern that you see can be attributed to amplitude modulations from mass accretion rate fluctuations. So you have these fluctuations that originate on the outer parts of the disk that then propagate inwards and modulate the QPO somehow. And On the other hand, the cross pattern can be attributed to variations in the optical depth of an accretion flow with QPO phase as it is processing. So what would this roughly look like? For example, in the web pattern, which we see when the QPO frequency is below 2 Hertz, you can think of a bit more of a truncated accretion disk. And if you have a geometrically thick accretion disk, this is able to support poloidal magnetic fields that can thread the disk and support radio jets, which we can then observe with optically thick radio emission. On the other hand, for example, when we see the cross pattern at higher frequencies, the disk can be thought to extend inwards more. And in this case, if you have, say, a geometrically thin accretion disk, the jets are quenched, explaining why there is lack of radio emission in this case. And finally, if we jump to the hypotenuse pattern, which, remember, this is kind of the weird one we don't expect, this is when we also have observations that have extremely high X-ray luminosity. So here, if the accretion disk puffs up due to radiation pressure, this is able to support jets. However, because the accretion disk is so important in this state, you can also think of there being a high influx of soft disk photons that are then intercepted by the jet. These soft photons can then cool the jet electrons, leading to optically thin radio emission.
1 minute left.
Perfect. And so this is partly why we can think of GRS 1915 as unique, because the cooling of the jet electrons by these disk photons only starts to become a factor at the highest X-ray luminosities. And so this is consistent because 1915 is one of the few sources that gets to these high luminosities. And so we have, a bit of a consistent story going on here. So to wrap up in my last minute, hopefully I've convinced you that the bispectrum is a very valuable tool for understanding X-ray variability from these kind of systems. In particular, I've focused on the bicoherence that can be used to probe phase coupling, but there is also the biphase, which Ed alluded to in his talk earlier. And in the case of GRS 1915, the bicoherence indicates that the cooling of jet electrons by disk photons could play an important role. And I will wrap up with that and take any questions. Thank you so much.
All right, thank you, Kavitha. Very nice. Are there questions? Yeah. Timo?
Okay, thank you. Quick question here. Why can't you just do the QPO, the straight coherence between QPO and the low frequency power fluctuation, some part of the low frequency domain there? Why you need to do 3 frequencies?
Because we're trying to see how the different the frequencies are coupled. So, for example, just to give a thing here, you can see. Go back here. So here, something I skipped over was, for example, this feature here. And this is, where both frequencies are the QPO frequencies. So if you're looking at the sums of frequencies, you can then tell that this is saying that there is interaction between the QPO and the second harmonic, which is, saying that, again, they are not generated independently. So when you're looking at triplets of frequency, you can start to probe those kind of interactions, which is kind of the big plus point of using the bispectrum.
So the sum of the frequencies, the QPO frequency, or the second harmonic of the QPO, which one is how do you choose the frequencies and the sum? I mean, if you choose the frequencies, the sum is obvious. So the question here is, how do you choose those 2 frequencies and their sum so that one of them is on the QPO?
Yes, so we don't just choose one particular frequency. We scan across the entire power spectrum. So this plot is essentially showing how every single frequency here is interacting with every other frequencies. And this is because there's this region where it's kind of like a peak. You can see, there's something going on there. And that is indicating interaction between QPO and harmonics. So we don't just pick a particular frequency of interest. We are scanning all these frequencies.
Okay, all right,
Okay.
thank you.
Good. Joey?
This is really interesting. Thank you for showing this. So one thing that I noticed is that you have this inclination dependence,
Yes.
and this got me thinking about Jakob Meneneinden's work showing that the phase lag at the QPO frequency is strongly inclination dependent. Is this the same phenomenon that you're detecting with the bispectrum, or is this? Is it a different perspective on the same thing, or is it something different, do you think?
I would say they're two different things, probably hinting at something similar. So for example, the fact that we see an inclination dependence in both the amplitude and the phase lag and the bicoherence, indicates that there could be some kind of geometric, that is more of a geometric phenomenon. But they are fundamentally looking at very different things. We did in fact look into how the bicoherence, does it have any effect on what the phase lags are doing? And I'll sum up by saying more data, please.
Okay, great.
Thanks.
And Riley?
Nobody in the room.
Oh, okay. Let's go to Riley next, and then we'll go to the room. You're muted, Riley. Sorry.
Okay, can I be heard now?
Yes, twice or 3 times.
Yeah, really nice talk, Kavita. I just wanted to, I guess it's just a general question for somebody who doesn't understand all the timing stuff too well. This bicoherence pattern you see, I think you said it was the cross pattern, if I'm getting that right, where this is telling you that the QPO and the broadband noise are not independent. How far can you go with that statement? I was just wondering, like, does this just mean, okay, they could be coming from the same region, or can you go further than that?
So I think I would say, rather than saying they are generated, they could be generated by the same process, or they could be, the same process influencing both of them. So that's kind of why we have an idea of, say, having either the fluctuations of the outer bits modulating the QPO, or you have the QPO itself modulating the noise. That's the kind of interaction I'm talking about, if that makes sense.
Yeah, that makes sense. It's a lot to think about, but yeah.
Yeah. It's just not that they are completely removed from each other. They influence each other in some manner.
Was there a question in the room?
No.
No. Okay. Well, let's stop there. Thank you, Kavitha. Appreciate your talk. Let's thank Kavitha again.